Then, Laura, thank you very much for introduction. Yeah, and to all of you, I must say this is a bit an embarrassing talk. Embarrassing because it's 15 years of work. We had at least 5 rejections, and still the answer we got is something which I still have doubts, and we might still have the inclination to have another go at it. The reason I'm still presenting this is also because I want to show that science is also about being able to swallow rejections and being able to carry on, even if you're losing track of things and maybe losing hope even of things. So let's see where we got. I hope to at least have a complete story and show you that if you move on and leave it aside for a little while and then pick it up again and collaborate with some people, you might at least have a story in the end. Now, what is the story about? Well, the thing we did, and I've been doing for a long time already, is in optical monitoring of the hydrogenation of thin metal films. And in thin metal films, you can have 2 phases, a phase where there's very little hydrogen inside, so-called alpha phase, and you have a beta phase, where there's a lot of hydrogen inside. Now, one of the interesting things is that it was found that if you have a metal thin film, you can watch this transition optically, even by the naked eye. And that means that here you see a reflective yttrium layer. And if we now change the hydrogen pressure of the ambient of this thin film very slowly, then at a certain point we enter in this dense hydride layer. And here you see it's now a trihydride, it's transparent, and there's a clear optical transition. And that means that we have an optical means to actually accurately observe this first order phase transition between the alpha and the beta phase of the metal. Now, that is very handy because you can do that at 1 temperature, you can do that at many temperatures. And then if you know your thermodynamics still, that you know that there is an equilibrium constant K, which is related to delta H and delta S. And if you plot it for a case like this, a magnesium reacting with hydrogen forming magnesium dihydride, then the equilibrium pressure of hydrogen is related to the change in enthalpy and the change in entropy between the left and the right hand side of this equation in the following way. And that means that if you plot, I need to use the, what is it? Probably, I can use the laser pointer. This is more clear. So if you plot now the plateau pressure as a function of the temperature, and now I've got a problem. Yeah, sorry, that's too fast. So if you plot the hydrogen pressure as a function of the inverse temperature, you see that the slope of this line is the enthalpy of formation, and the where it crosses the abscissa, you have the entropy. And again, these are the enthalpy and entropies of this reaction. So it's an enthalpy change. Now, the fact that we can observe this optically allows us and gives us the reason to go for these, to observe these transitions in a combinatorial sense. Now, my PowerPoint is not responding. Sorry. This is probably not a wise, I probably have to restart it. Oh, there it comes. So let's hope it keeps on moving. So here we have our machine. Herman Schroeders made that already a long time ago when we were still in Amsterdam. And this is a sputter machine, and you have here a sample in the middle. And if you have asymmetric deposition sources, you form gradients on this sample. And that means that you actually make a kind of phase diagram. On one side of the sample, you have a lot of titanium. Here you have a lot of nickel. And here you have a lot of magnesium. So you can make a lot of compositions in one go, meaning at similar deposition conditions. Now, the fact that you can also look at them optically allows you not only to make them in a combinatorial way, but also analyze them in a combinatorial way. And you do that by putting the sample into a box. And this setup was developed by a PhD student back then. That was Robin Gremaud. And after his PhD, he went to ABB, and he is now a researcher, senior research staff at ABB in Zurich. So what do we have when we have such a machine? Well, we have a box, and basically through the box, we have a light source shining. And in the box, we have put our sample, and we can change now within this box the hydrogen pressure very slowly. And what happens if we do that, we can see the transition occurring locally, meaning that we can determine the equilibrium pressure for each point on the sample separately. And that means that we have a kind of map of all kind of deposition pressures. And if we transform this composition map to a ternary phase diagram, we have here a mapping of all the equilibrium pressures where the hydrogen is going into the metal. Now you see also a black part. Here we were not certain whether this is a real equilibrium pressure, but the colored parts are really straight, very well-defined first-order phase transitions. And you can see we have now hundreds of equilibrium pressures measured in one go. So no uncertainties in terms of pressure and temperature between the samples separately. That's the big power of doing a combinatorial experiment. Now, if we have this pressure measured at one temperature T1, we can do this at several temperatures. And in this case, we did it at 5 temperatures in order to make Van 't Hoff plots for all these hundreds of samples. What we then got was this, a plot of the entropy of formation of the hydride and the enthalpy of formation of the hydride. And from the color scale, you see that there is a correlation. It seems like when the entropy goes up, the enthalpy goes up. And that's very strange. It's also something you worry about. Is this correct? Did we something wrong? But if true, what is behind it? What is the physics of this? Or what is the chemistry of this? And the guy who first looked at this was actually Chase Broeders in 2006. He was a bachelor student with me working on this. And Chase was a brilliant student, got his cum laude each time, and he is now an associate prof at Free University in Amsterdam. So he also was worried very much. He did a lot of work on that and tried to figure out what is behind all that. We failed. We showed this to colleagues, and the colleagues said, well, no, this is not really it. Even if we showed this curve where we plot, say, in more visual terms, the correlation, we actually observed correlations in 2 sets. You could say a B set and an A set, and you see very straight lines between the entropy and enthalpy of these sets of samples. Why did our colleagues say this is wrong? And the reason for that is basically that they say, well, the temperatures, actually my computer is blocking again. I think I go out of presentation mode. I'm afraid that this is costing too much. Let's see whether I can do that. Okay. It is still blocked. Let me see what I can do. I'll restart the program and then kick out presentation mode because I think that's too much. You got the conclusion now. Escape. Okay. We were at this slide. Do you still see me? I mean, do you still have a...
We see, I personally see the first title, the title slide.
Okay,
I don't know about
yeah.
that one.
I will move it on then. Why does it not work? Okay, I try it like this.
Bernard,
yeah.
If you are connected to any hub or Thunderbolt thing to your laptop, that could cause a problem. If you detach, then because your machine reduces the processor power to about 60% at the smallest rate when it's connected. So as soon as you disconnect your desktop monitor or whatever, it can give you the problem.
Okay. I try now this. I've got presentation mode, out of presentation mode, just a direct mode. Maybe that works better. So my reasoning stopped here, and what we see here is that these straight lines then relate an enthalpy-entropy ratio of 400K and 300K. And now this is within or just at the border of the measurement range of temperatures we measured for these experiments. And that is actually the reason that colleagues told us and said, well, you shouldn't really look at that. And I didn't at first understand this reasoning. However, if you do, maybe before I go there, sorry. So if you go a little bit further than this, I didn't understand it because this is such a good fit. You have an R square of 0.998, and you have a very straight line showing a very good correlation of a particular set of data of this magnesium nickel titanium hydride. And if you look at the ternary phase diagram, you see it's also a particular set of compositions which have this kind of behavior. Now, why is this? And the question is it worth to investigate? And the colleagues say, no, it's not worth it. And the reason for that is if you do a simulation, and this is a simulation for 8 samples, taking a certain kind of enthalpy, you have a certain slope and you vary around that slope, and you can make big variations, small variations. It doesn't really matter for the argument you're using. Basically, what you have is curves like this. So you can do, in this case, 4 simulations. You can do 5,000 simulations. The outcome is more or less the same. What you have is, in this case, you get straight lines. And these straight lines have amazing R squares. So even if you do random experiments, and these are random simulations, you get a very good R square. However, you also see that your compensation temperatures are all a little bit around 350. And the more simulations you do, you will find more and more temperatures also at more extreme values. So that's basically the reason not to go into that too much. However, of course, this is something, I wasn't really happy about. And again, my computer is blocked. Oops. I'm afraid my presentation is a little bit too heavy on the... shit. Shit.
Hi, Bernhard.
Yeah.
Use the keyboard to go forward and back. When you use laser pointer, you can't do this with the mouse anymore.
Yeah. And so what were you suggesting?
try it with the keyboard with the arrows. We're going forth and back.
Yeah, okay. Okay. However, these straight lines, there's another thing, and that is something we came across, and we can only show that in a different kind of sample. Now it's again ternary, quaternary sample, magnesium, titanium, aluminium, and there's something other which is related to what we observe here, and that is, do you see the mouse, by the way? And I'm using the mouse, maybe it's better.
Yes, we see it.
Okay, so what you see is that not only do we have correlation, but we have also so-called isoequilibrium points. And this is actually related. So you see here a large compositional range where the equilibrium pressure of all these samples is exactly, well, more or less the same. Why would that be the case? Well, at equilibrium, we know that TdS is TH because we have an equilibrium and these two values should be the same. Now, in case of a compensation, this should be the same for all values I, so for all samples. And because that's actually what the slope of the compensation temperature tells us. Now, if we go back to the Van 't Hoff plot, we observe this relation. And if we now combine these two, that means that at the compensation temperature, the Van 't Hoff relation can be written like this for all samples I. Now, this is a bit complex. Maybe just believe me, the log over P over the standard pressure gives us a constant value for all samples. Now, this is exactly what we observe. So we're observing actually for all samples x1 to x4, we observe that this pressure is the same. So, and that is actually the result of this compensation. Now, this is an interesting effect, actually, because then it means that the enthalpy varies without a change in plateau pressure. Now, for our kind of applications, this could be very interesting because you do not always want to have the same amount of heat going in and out of your reaction. So by going into this temperature, you may tune the amount of heat which is going into your reaction by taking the appropriate value of your X of your sample. So taking the appropriate sample, you can play with the enthalpy without playing with the equilibrium pressure. Now, these were all very complex samples, and that is the reason that we went to a simpler sample, and that is a binary metal, magnesium titanium hydride. The magnesium titanium hydride, we have also been looking at that for a long, long time. And we had indications that indeed we have here a sample where we have islands of titanium in magnesium. So the blue is the titanium and the yellow is the magnesium. And actually these islands are very, very small, but they remain present also if you do reversible hydrogenation. So we have a single phase, which is an FCC phase of magnesium titanium hydride, where we have islands of very small, 3 nanometer of titanium in a matrix. So this is a well-characterized set of samples, and actually we do exactly the same. And here, this is the same setup, but now we have a linear sample with a linear gradient, so we don't have any trouble to identify which part of the sample has which composition. And these experiments were Christian Boltzmann, who did those. And also Christian was a PhD student, actually working very long time on this, but luckily he had a lot of other papers as well, but he couldn't turn this into a paper. But it was a beautiful chapter in his thesis, nevertheless. So what did he find? Well, again, now you have the hydrogenation in your sample, and again, he did it at different temperatures and pressures. And you can see again, these are the equilibrium pressures, very nice, straight, flat plateaus. And here you see a very nice Van 't Hoff relation. indicating an enthalpy and an entropy, which is having quite reasonable values. Now, if you look at all the samples, it looks a little bit more wild. You see that not all the plateaus are as flat as all in the beginning ones, especially the magnesium-rich plateaus are very straight. And then the question is, which is now my equilibrium pressure? And then we took simply the pressures along this dotted line. You can take other choices. Basically, the argument remains the same. Only the values change a little bit. And what we observe here, maybe that's the most important part, is that at low temperatures, the magnesium-rich have the highest equilibrium pressure. And here, at higher temperatures, the magnesium-poor have the highest equilibrium pressures. Now, this points already to a little bit like a composition behavior. And indeed, if you look at the correlation between the enthalpy and the entropy, we see a beautiful straight line. And again, the correlation is very, very good, but also the R square is very good. It's 0.9995, which normally would say, well, this is good enough for me. Again, the meaning of this composition temperature means that this ratio of enthalpy and entropy of the reaction is the same for each composition. Yeah. Now I have to say something else, which is a bit strange, because in principle, if you look at this kind of reaction, magnesium, maybe a magnesium alloy, magnesium X plus hydrogen, gives you this magnesium hydride, you would expect that the entropy of this reaction is fully determined by the hydrogen. So you lose 130 joules per K per mole, because that's the entropy of hydrogen in the gas phase. The entropy difference between the solid magnesium and the solid magnesium hydride should be very small, and should be very small if you take the difference between the two. So actually you would expect these kind of lines, all straight and all ending up in this point at 130 joules per mole. Okay. Actually what we observe is something like this. So that shows us already something. We don't understand all of this reaction, and particularly we don't understand the entropy even of the most simple metal hydrides like palladium hydride, for instance. This is very hard to actually calculate. Before, I just told you is that what we expect if we have a compensation effect, we expect a point, an equilibrium point, an isoequilibrium point like this. Now, if these lines are all tilted, this may be a little bit hard to observe. So what we did is we straightened up these curves, and that we did by taking the difference between the equilibrium pressure and the average equilibrium pressure. And then you get the same kind of isoequilibrium point, but it's more visually attractive, I would say. And if we do that for this series of magnesium titanium hydride, you indeed see that there is a minimum, not really a convergence, but there is at least a minimum at this composition temperature of 470 K. And these lines go widen out at lower temperatures. And here's a little bit smaller range here. But you see that there is a minimum. And of course, you can never have an exact point, because that would mean that your experiment would be perfect. There would be no noise in whatever parameter you're measuring. And this is, of course, only true in idealized cases. But of course, we would like to know, is this now a minimum which is worth considering? Is this now a true minimum? Is this a minimum which is strong enough for us to consider it to be a true compensation effect? That is really the point I'm trying to bring you to. And before doing that, I first have an alternative experiment showing again the difference and how difficult it is to come to a clear answer to that. These are our Swedish colleagues, Sirenova, and they work on palladium nanocubes. They're very small. They can be made between, say, 18 and 16 nanometers. And then, of course, because of the size effects, you can understand a certain effect of the entropy and the enthalpy on the size, or the size on the entropy and enthalpy. And indeed, they observe it, and there's a really, again, a compensation, but you also see there's a lot of noise here. But let's have a look. Again, you observe that this compensation, if you plot delta H and delta S, is not at all bad. I mean, you would yeah, it still has an R-square of 0.979, so it's not altogether bad. However, if you now look for this isoequilibrium point, you see it's quite a different situation. Here, that's hardly discernible. It should be somewhere here, and it's hardly smaller than what's happening in this area. And actually, the yellow area is the temperature range where actually the measurements were being made. So if we now plot this LNP spread, and we just plot all the hydrogen's pressures, which we plotted basically on the basis of our Van 't Hoff plots, we see this curve and we see a minimum. But the minimum is not very, very distinct, I would say. And if you compare that to the minimum in the spread of LNP for the magnesium titanium, you see quite a difference. Here you really have the feeling that you can discern the minimum quite well. Now, what is this minimum? And I don't like math very much. I'm not very good at it. So here comes in Ronald Greason from the Free University of Amsterdam, and he is my former boss in Amsterdam. So then it's always good to check out on him. And then he figured out that this LNP spread is actually the variance of LMPT, the square root of that. And this variance, yeah, you can just get it from your calculator based on the data you've obtained of all the pressures and the pressures you have calculated based on Van 't Hoff relationships. However, the beauty is that you can also get this variance analytically from the enthalpy and the entropy, now in the reduced form H over R and S over R. So this is really the point, because in the literature, you often don't see pressures, equilibrium pressures. You see, I have made a beautiful plot correlating the enthalpy and entropy. So to have a trick to convert the enthalpy and entropy into this variance is very powerful. And this is again the math where I give you the equations, but I won't go into that. Suffice to say that, so the variance in the enthalpy is simply the difference between a particular enthalpy minus the average enthalpy, and then squared it and summed it over all the samples you have measured. And the rest goes similarly. What does it mean is that you can, now maybe first, the next step in the calculations, because I have now a feeling for this spread in my minimum, in my isoequilibrium point. And the question now is, which spread is acceptable? Which one is so small that you can accept it as a real indication for a physical entropy relationship? And for that, we proposed the following, and that is compensation quality factor. It's always nice to try to impose your own acronyms on the literature, but of course you're very often disappointed that nobody copies it. But again, let's wait and see, maybe in 20 years. So if we have a compensation quality factor, which is 1 minus the variance, the minimum variance, and the maximum variance. Now, what is the minimum variance? That is the variance at the minimum. And here we plotted it, so it's the variance at this minimum point of the curve which we calculated, or either analytically or we plotted it based on the calculated Van 't Hoff plots. And we compare that to the maximum variance, and that's the maximum variance observed in your measured data. And you can either do it directly from the equilibrium pressures again, or you can do it analytically from the enthalpy and entropy values. And then what you observe, these are the data of your palladium nano cubes. These are the data of the magnesium titanium hydride samples. And then you see a clear difference in magnesium and titanium nano gradient sample. You have a CQF which is really large. And then you could say, yeah, this is a bit arbitrary. Why should it be 0.9? Why can it be not 0.8? And indeed, this is a good question. The reasoning we had at first is that we said, well, this minimum, we have to compare it to something. And then it's reasonable to say, well, let's compare it to the largest spread in the data. And then a factor 10 should be good enough to suppose that this is really something which is beyond a statistical effect. That is basically the starting point of the reasoning. But of course, you can go further again. You can just say, well, let's do again simulations. And then here are the simulations again counting now. These are thousands of simulations, and they count the times that we observe a compensation quality factor of 0.5 or 0.9 or 1. And then you see that depends on the number of samples you take. So for instance, if we have 8 samples in this upper right corner, and this is the cumulative percentage, then you see that if we have something like 0.8, it is very small percentage, let's say smaller than 0.05%, that this is the result of an average of something which is statistical. And the same holds for the other samples. And then you can make a kind of curve and say, well, depending on the number of samples, you have a compensation quality factor, even if it is only 0.6 or 0.7. Well, maybe then it is still not statistical. The only thing is that then the width of your isoequilibrium pressures is not that good. It's only a fraction, maybe half of the width of what you typically observe in your samples. So that makes now a distinction. On the one hand, we have something which is not statistical, but on the other hand, you do not see a clearly defined isoequilibrium point. So actually what we did is we splitted the compensation effect in 2 effects. One is a relation between enthalpy and entropy statistical or not? And the other, do we observe something like an isoequilibrium point? And depending on what you're heading for, it is worth going or not. And this whole point is what's happening here. If it is not 0.9 or higher, but lower, I don't know. Actually, this is still, for me, an open question. But in order to make this point maybe more clear, so for instance, I showed you before of the magnesium nickel titanium hydride samples, these plots. Now we can pick another sample fraction. These are all the samples on this line, so we have the same kind of magnesium fraction. If you now plot the enthalpy and entropy, you see this kind of curve. Now I would say also this cannot be a statistical effect. But however, it's not a linear non-statistical effect. So apparently in this whole zoo of enthalpy-entropy, there's a lot we don't understand. And there's a lot of relations we don't understand, which at least have, from the basis of this analysis, you cannot simply discard by, oh, this is statistical. It could, of course, be a standard measurement error, some kind of standard issue which you do wrong. But that is exactly where further research is needed, which goes beyond the topic of this talk. There's one more thing, because I know there's a lot of people doing kinetics. And in kinetics, you're doing Arrhenius plots. And Arrhenius is actually the same as the Van Hoff relation. So if you have this K is a prefactor times the exponential of the activation energy, you can easily write it like this, and then you simply substitute the enthalpy for the activation energy, and here the entropy. And of course there's logic, because also this kinetic relation is related to the same thermodynamics where normally for the activation energy you put delta G. Now, here we have a kinetic example. These are all kinetic hydrogenation of various magnesium-based hydrides. And there's 8 of them, 8 different spheres. And you see there's a reasonable relation. But here you can easily discard that now. You see that these are the LNK minus the average LNKs. Here again, we plot the width. And even without doing the calculation, you can see there's hardly a minimum here. And indeed, the CQF is 0.16. So definitely something you can forget about. Now, in the beginning, I showed you this plot, fishes. So what has it all to do with fishes? And actually, there was an old Nature paper, and a Nature paper of 1975, claiming an enthalpy compensation effect in the activation energy of an enzyme in the white muscle of a certain fish. I don't know teleos fishes at all, but apparently there are several of them, seven types of them, and they all inhabit various waters from the Antarctic to tropical waters. So what they did is they looked at the kinetics of this enzyme reaction, and they looked whether they could find a correlation like this. And indeed, again, now this is a kind of, there's a plus here because actually it is determined from kinetics. So it's not exactly the enthalpy. But apart from that, you see here a beautiful straight line again. And now, again, we have an R square which is large, great enough. I mean, it's good. However, now again, we do the same trick as we did before. We have now the spread in the prefactor, or no, the spread in the delta G over RT, which is something like the delta H, or no, I'm saying it wrong. This is something like the spread in the LNP we had before, and we plot it versus the inverse temperature. And again, we take the minimum in the minimum of the curve, and we compare it to the maximum spread in the samples. Now, in this case, we didn't have the kinetic data. So this curve now is fully based on the enthalpy and entropy values. So without even looking at the actual kinetic data, we can find and analyze these data. And we find, yeah, it's a sizable CQF, but it's smaller than the critical value which we set. So here's the fake. It's high enough to say this cannot be statistical, but it's lower. It's too low to consider really a minimum or a discernible minimum, I would say, in the or a minimum which is small enough to speak of an isokinetic point. Now, the last point, last slide, is why would we have compensation at all? And there's tons of papers. By the way, about this topic, there's thousands of papers. And also in our lab, I know Evgeny Pitko has published something, Michiel McKay, Wim Haije, Volker Mulder. Many people have dealt with this kind of relationship, but actually I haven't found really good examples of it. And the only thing I would say is that the Van 't Hoff relation, as you see it here, is of course a strange one, because here the temperatures, the delta H and the delta S are of course temperature dependent. And these temperature dependents have different relationships, and they do not, these temperature dependencies do not have to be the same for all samples. Maybe there is a trend in the temperature dependencies of these CPs and CVs. But even there, people have tried to get there, but to my knowledge, not in a very successful way. And that means that I have seen no clear or proven compensation mechanisms that really have been confirmed by real good examples. So that brings me to the end of this complex talk. Even when talking this through, I'm bewildered a little bit. But I hope what I've shown you is that compensation effects are not necessarily due to statistical effects. So if somebody comes to you and say, nah, don't look at it, it's always statistics, don't believe him. Even when compensation temperatures falls within the range of measured temperatures, you don't need to assume statistical effects. Now, what I find interesting is this isoequilibrium points. I think that's an interesting one, and we found a way to determine the spread about these isoequilibrium points and isokinetic points analytically. So you don't always need to go back to the data. And we define a compensation quality factor to define the size of the spread, where you can determine for yourself, basically, is this spread good enough for me to have a further look? And then this whole issue is indeed only above 0.9. I think you can speak in a true compensation sense. What happens just below that, for me, is still an open question. So with that ends my talk. I'd like to thank all the co-authors and all the people who contributed to this talk, and I would like to thank you for your attention, and I hope at least some of these messages have come through. Thank you very much.
Thank you, Bernard,